We're entering the home stretch, but we still have a lot to cover. We've learned about the drives that make applications move, and we've explored the I/O devices that are their arms, legs, and senses. Now it's time to take a deeper look into what controls them and the ways they communicate. Let's go. Hopefully, you remember this industrial automation system hierarchy diagram from Module 1. The past three modules have focused on the lowest level, field devices. Drives and I/O devices live here. We're about to move up a level and explore local control, the place where we'll find various kinds of controllers. Local control's scope is often a single machine. That machine will contain various field devices, such as one or more drives to make things move. The operator will use an HMI to control the machine. I/O devices like sensors monitor the process, while actuators produce additional movement. Status devices and controls give the operator additional ways to monitor and control the machine. But these devices can't function in isolation. Unless they're connected into a unified system, they're useless. The machine's controller and its field bus work together to perform this vital role. The controller orchestrates operations while the field bus connects everything. The controller is a small industrial computer running a control program. The field bus is an industrial network that provides the communication infrastructure for all the devices making up the machine. The controller sends commands to the machine's drives over the field bus. I/O devices may connect directly to the controller or they may communicate with it through field bus connected I/O modules. Let's examine a real system. This fill and seal packaging machine is a classic example of local control. The machine fills small airtight packets with product, seals them up, and cuts them apart. Finally, they exit the machine on a conveyor. The machine includes multiple drives to move the mechanical components, sensors to provide essential information, and operator controls for the employee running the machine. We'll examine these in a quick walk around. The signal tower reports the machine's operational status at a glance. The touchscreen HMI, as well as several control buttons, give the operator easy control. A drive, in this case a servo gear motor, provides motion. Two stepper motor actuators perform the complex motions that fill and seal the packets. As we walk around to the other side, we discover two more drives, also servo gear motors, that move other sections. An optical sensor detects the product as it moves through the machine. Another optical sensor helps control the packet material feed system. All the control and communications electronics are in the cabinet that makes up the machine's base. Let's look inside. The small SEW Eurodrive controller orchestrates every machine operation. It manages the three servo gear motor drives through their attached MoviTrack Advanced VFDs. The controller has no built-in I/O, so it connects to the machine's many I/O devices through multiple I/O modules. These can handle simple digital devices like buttons and sensors, but they can also control more complex devices like the stepper motors, which have built-in encoders. Although it's a little hard to see in the picture, a field bus links everything together, including the operator control HMI. Pretty nice. Original equipment manufacturers have many choices available when selecting the machine's electronics. A machine's key automation components may be sourced from a single manufacturer or pieced together. Going with an ecosystem has some definite advantages since everything is guaranteed to be compatible. Piecing a system together from multiple manufacturers, however, often provides greater flexibility or an economic advantage. Since the controller is the system's heart, choosing a controller type and brand is crucial, with machine designers often having definite preferences. Programmable logic controllers, known as PLCs, are the most popular controller type. Unlike general purpose computers, PLCs are specifically designed for the industrial environment. They're industrially hardened so they can handle dirty, hot, or harsh environments. They have lots of flexible I/O, which means they can connect to digital and analog devices of all kinds, as well as specialized equipment like stepper motors and their attached encoders. PLCs include reliable communications so they can talk to standard field buses. Crucially, they offer very predictable cycle times so the programmer can ensure that time critical events happen right on schedule. And finally, they're programmed using methods and tools oriented to industrial control. In contrast, an ordinary desktop PC isn't a great choice for industrial control because it lacks many of these qualities. It can't handle a harsh environment, and it doesn't connect to industrial I/O devices. And while it's probably faster than a PLC, its operating system isn't designed to give the guaranteed cycle time that many industrial control situations require. All PLCs include four essential elements: a power supply, a central processing unit or CPU, a communications unit, and I/O. With an all in one PLC, these will be contained in a single enclosure. All in one PLCs are usually aimed at smaller tasks because they have limited CPU power and I/O. They're perfect, however, for many local control tasks. Modular PLCs, like the one shown here, have individual modules that fit into slots in a machine rack. This PLC includes a power supply module, a CPU module, two communications modules, seven I/O modules, and three more communications modules. Modular PLCs are much more versatile because the machine designer can install modules to meet the application's exact needs. Some modular PLCs have enough capacity to handle multiple machines or even manage a system of machines. While there are many PLC brands, the four most popular tend to be Siemens, Rockwell Automation, Mitsubishi, and Schneider Electric. Automation developers code PLC applications using one of five standardized languages. By agreeing to use standardized languages, the PLC industry reduces the learning curve for programmers moving from one PLC brand to another. Collectively, these languages go by the name IEC 61131-3 and include ladder diagram, structured text, function block diagram, sequential function chart, and instruction list. Each language offers a different approach to solving application challenges, and PLC programmers usually have favorites. Some large PLC based systems may include multiple programs developed from more than one language. Ladder diagram programming goes back to the early days of PLCs. Programmers were replacing relay based controllers with PLCs, so the language was graphical, representing the program as circuit elements such as switch contacts and relay coils. These fit between two vertical lines like rungs on a ladder. Ladder diagram programming is still very popular, particularly with Allen Bradley equipment. Structured text, in contrast, is a traditional text based programming language like those used to create general purpose PC programs. It's especially popular with Siemens equipment. The PLC manufacturer supplies the development tools for its PLCs. For example, SEW Eurodrive's software package for its Movi-C product line is called Movi Suite. It includes the CodeAssist PLC programming environment and supports all five standard PLC languages. Unlike the very expensive development tools that other PLC manufacturers offer, Movi Suite is free. PLCs aren't the only way to control a machine. Many automation equipment manufacturers offer controllers designed to pair with their equipment. Manufacturer-specific controllers are targeted at particular applications. For example, SEW Eurodrive's UHX65A controller pairs with its VFDs, offering a powerful combination that can do very sophisticated drive tasks like robotics. This MoviDrive modular unit is actually 5 VFDs sharing a common power supply. The controller communicates with them over a field bus, which SEW calls a system bus since it links its devices into a powerful system. SEW Eurodrive's Movi-C system bus goes by the name S-Bus Plus. Some controllers have built-in I/O, while others use external modules like those found on modular PLCs. This SEW Eurodrive UHX65A controller, for example, pairs with multiple DIN rail-mounted I/O modules over its S-Bus Plus system bus. Some manufacturer-specific controllers behave like PLCs and have similar programming methodologies. Others have custom programming methods and tools. A third choice is becoming increasingly popular in industry. Some manufacturers offer pre-built, customizable application modules. These allow non-programmers to incorporate automation code into their controllers just by answering a few questions and setting essential parameters. SEW Eurodrive's Movi-C product line includes numerous application modules which go by the name Movi Kits. These implement automation tasks for speed control, positioning, complex motion, synchronized operations, and robotics. Industrial PCs are yet another controller choice. They're industrially hardened so they can survive harsh environments. Most are much more compact than general-purpose PCs. Sometimes they're incorporated into a PLC-type controller, like SEW Eurodrive's UHX85A controller, which is actually two controllers in one. Industrial PCs may run a standard operating system like Windows or Linux, or a specialized control-oriented operating system. Specialized operating systems enable PCs to handle time-critical tasks reliably. Automation programmers have countless development tools available, ranging from standard ones used to create ordinary PC applications to highly specialized ones. Industrial PC programs can be graphical, a definite advantage when HMIs are involved, and the computer can run multiple programs at once. It's even possible to run the development tools right on the industrial PC, making debugging and testing easier. Finally, another advantage of industrial PCs is that they can easily interface with enterprise management software. As we'll see at the end of this module, this feature is a key aspect of Industry 4.0. Okay, enough about controllers. Let's talk about how Fieldbuses work. While there are many Fieldbus standards, they all share common qualities. The Fieldbus links devices together, like this controller and VFD, so they can communicate. In most cases, the communications medium is a cable, but error is possible if the Fieldbus uses wireless technology. Data travels over the Fieldbus serially, one bit at a time, in other words. The network hardware takes care of sending and receiving the bits. Each Fieldbus technology has a speed rating called bandwidth. The Fieldbus bandwidth is the number of bits that can travel over it per second. Older Fieldbuses have bandwidths rated in kilobits per second. A kilobit is 1,000 bits. Newer Fieldbuses have much higher bandwidths, megabits or gigabits per second. A megabit is 1 million bits, while a gigabit is 1 billion bits. Every Fieldbus has two layers that define its functionality. The first includes all the network hardware. This includes the cables and connectors that link everything, as well as the circuits and electrical specifications that produce the signals. The second layer includes all the network software that controls how the bits travel over the Fieldbus. The software manages details like addressing, how devices tell each other apart, and protocol, how they communicate. It also deals with detecting errors, maintaining security, and routing traffic between different field buses. And yes, for you network geeks in the audience, I realize that this is a very simplified picture of how networking operates. Okay, let's cement these ideas in place by examining the most popular field bus standards. As you'll see, they share many features, but also have subtle differences. Modbus is the first example. It uses industrial Ethernet as its hardware side. As you probably know, Ethernet is the network standard used in many offices. Industrial Ethernet is compatible with standard Ethernet, but has been modified to work more reliably in harsh environments. Modbus uses a very common network protocol called TCP/IP, along with a specialized one called Modbus TCP. Our next example is Ethernet IP. It too uses industrial Ethernet for its hardware side. The software side uses TCP/IP and a specialized protocol called CIP, which stands for Common Industrial Protocol. Ethernet IP field buses are especially popular in Rockwell automation systems. The third example is Profinet, which is very popular in Siemens systems. It uses industrial Ethernet for its hardware side. The software side is a bit unusual, however. One side handles communication that isn't time critical. It has two parts, TCP/IP and Profinet (NRT). The other side has just one protocol component called Profinet RT, which stands for real time. By having less software overhead, this side can communicate more rapidly and predictably. This is probably a good time to define what real time means. A real time system responds to events very quickly and predictably, usually within milliseconds, thousandths of a second. Many industrial control applications require real time response from the control system so events happen correctly and safely. A system that doesn't respond in a predictable amount of time or that takes too long to react could cause dangerous accidents in the processes it controls. The fourth example is another field bus that excels in real time control, EtherCAT. It uses a specialized version of Ethernet designed to be both fast and predictable. Like Profinet, it has two sides, one for communication that doesn't have to be real time, and one for communication that does. EtherCAT is so quick and responsive that SEW Eurodrive uses it as the basis for its SBus Plus system bus. Our final example is an older field bus standard called Profibus. It too has been popular in Siemens systems. Profibus uses RS-485 for its hardware side. This makes it a much slower field bus than those based on Ethernet. For its software side, it uses a protocol called Profibus DP. Profibus is a legacy field bus developed in the 1980s but still in active service. For this reason, many manufacturers, including SEW Eurodrive, still support it. Every field bus uses an addressing scheme to identify each device. If it didn't do this, there would be no way for controllers to send commands to or receive responses from specific devices. Let's see how this works with a small field bus containing one PLC and three VFDs. We'll start with Ethernet IP. In this system, each device has a unique IP address. You may already be familiar with these four-number addresses since networked home and office equipment use them. Profinet uses IP addresses too, but also requires each device to have a unique name. Profinet device names are usually descriptive as well as unique. Notice that each name identifies the device's function in the system. Profibus, along with most older field buses, uses a unique device number as the address. Usually these are set by physical switches on the device. Profibus addresses are numbers from 0 through 127. So how do devices talk to each other on a field bus? We'll go back to our Profinet-based system and see. Devices on the field bus exchange process data words, called PDs, to control each other and report status. For example, let's say that the PLC wishes to tell the loader VFD to start turning clockwise at 1000 RPM. It would create the necessary process data words and then launch them onto the field bus using that VFD's Profinet name as the address. The VFD then sends back process data words to the PLC confirming that it's now running. Simple but elegant. Up to this point, nothing we've examined is different from what was available in the Industry 3.0 days. Now let's take things past Industry 3.0 to Industry 4.0. To do this, we add three more layers of control above the local control level. We'll start by examining mid-level control. In an Industry 4.0 plant, we have lots of smart machines containing the kind of local control that we've been studying. But instead of being little islands all by themselves, they're now connected to a plant field bus. Larger PLCs and industrial PCs exercise control over these machines. We call these upper level PLCs because they don't deal with the nitty gritty details of machine control. Instead, they just issue basic commands to the PLC within each machine and let those PLCs deal with the details. Industrial and ordinary PCs connect to the field bus. Plant personnel use them to manage and monitor individual machines. HMIs communicate over the field bus, providing personnel with control and monitoring points throughout the plant. Wireless routers allow personnel to roam around the plant using untethered tablet and phone devices. As you can see, communication is the heartbeat of Industry 4.0. To really achieve its potential, however, Industry 4.0 needs to go beyond mid level control. Communication needs to extend to the entire IT infrastructure within the plant, and then it needs to expand to the entire corporate IT system. To do this, we link the plant field bus to the plant IT network. Unlike the plant field bus, which primarily deals with plant machinery, the plant IT network deals with almost every aspect of the business. Devices on this network include file servers, printers, and countless users on ordinary desktop and notebook PCs. Wireless devices access the network too, performing countless everyday tasks like messaging and collaboration. Specialized AI tools connect at this level, and of course, the global internet. Large companies will have many geographically distant facilities, each with its own IT infrastructure. But these can communicate easily as long as they're on the global internet. In theory, at least, anyone within the company should be able to communicate with any other device on the network. Corporate enterprise resource planning software can integrate with and oversee the entire operation. That's the point of such thorough connectivity and the basis of Industry 4.0. Now, before we get all excited by this tale of a technological utopia, we need to apply the brakes and consider the risks. Obviously, strong security is essential since malicious activity can have serious consequences to Industry 4.0 facilities. By making every device potentially reachable on the network, we open the door to sabotage, malware, exploitation, and theft. For this reason, Industry 4.0 also requires some very heavy duty IT expertise to prevent unauthorized access by unauthorized personnel. Tools like firewalls, anti malware software, encryption, and robust access control systems help ensure that only the right people performing the right kind of tasks can access specific sections of the system. As we know, however, no security system is bulletproof, and the early history of Industry 4.0 already contains some fascinating and frightening stories. Despite this, the strong advantages offered by Industry 4.0 make it the path that many industries have committed to follow. Time will tell how it all plays out. And on that note, We've completed our journey into the world of Industry 4.0. You've learned a lot about industrial automation and Industry 4.0. If you took this course as a prerequisite to another class, you'll need to take the final test. It may be administered through a learning management system, or it may be a PDF that you fill in and submit. If you took this course just to learn more about Industry 4.0, we certainly hope that you found it helpful. In either case, SEW Eurodrive's training department wishes you well and hopes to see you in other classes, both online and in person. Have a great day.